Welcome back, everybody. I'm so excited today to provide you another video of my online teaching. In this video, I would like to show you the new topic, which is rational function in the course of pre-calculus, Math 12. So this video will give you an idea of how to sketch a basic rational function. There are a lot of information and details in this topic we will explore together. However, before I get into the topic, again, please let me introduce my mathematics courses online. I have been creating and developing for more than 3 months, including the first introduction to calculus course, second introduction to calculus course. The full set of course has been reduced by $80 US now. So including the 100 of my video teaching lecture that led you step by step, it's so cheap compared with private tutoring one-on-one. You will be charged for $100 or $60, $50 an hour at least. So online education provides the opportunity for all of us, all the students, bring the gaps of inequality in education and provide you an individual one-on-one teaching online. Even though I'm not there to tutor you, but you register in my course online, you will have full support from me if we book a Zoom advanced lesson online. If you book in advance, I will be there to help you for my courses. So get into my courses online. My math teaching dossier is my website, and if you want to purchase the full set of my math courses online, go to mathcourses-online.teachable.com. I wrote it on the top of my border here. I am a certified high school math teacher in Canada, and in the past, I have also have experience teaching and tutoring in both US and Canada as well. So I hope that during the pandemic, our education will not be disrupted. And I would like to provide the online education opportunity to all the students across the globe. It's just not here in our North America because mathematics has one universal language. So you can learn from everywhere, from Asia, Middle East, like every country around the world. And I hope that my contribution, my sharing passion and my knowledge and contribution to our global education. So I am done my advertisement. So thank you for watching. Let me get right into the lesson now. So the topic today, we're talking about the rational function. What is the rational function? Now, in elementary, you have learned that any fraction, for example, 3/4, or maybe 1/200, so on. Any fraction we call rational numbers. It could be rational or irrational, depend on how many repeating number we have it. For the decimal, if we divide the top by the bottom. However, we are in algebra 2. which is high school, our math progressed to a higher level. So in rational function is actually the same like a fraction with the numerator on the top and denominator at the bottom, except that each numerator or denominator, or both of them, or maybe either one of them, will be a polynomial, which is involving an algebra expression, whether underneath the expression or on the top. For example, this one here we call a rational function, and this one here we have both algebraic in both numerator and denominator. Sometimes it could be in a factor form like that. Now the basic one we will learn today will be something like y equal 1 over x. And this is the basic symbol rational function. And you can see we call it a rational function because we have a denominator is a letter, even though it's just one letter. It could be 1 over a, 1 over b, whatever we call it. And long as this is an unknown number, it's an x. So this one we call a function because it's rational function because it's in the form of a fraction with the denominator have an unknown number. And that's why we call this a rational function. There are a lot of things we need to know about this rational function. So first, let's talking about the basic one here, the basic form y equal 1 over x, before we even get into this stuff here. So the basic rational function is 1 divided by x. Now in elementary school, or even in high school, we learned that any fraction only valid if we have 3 over 4 like this, or maybe 2 over 7, blah, blah. Or even though 0 over 5. And the reason because we can divide this number, right? So even the numerator is 0, the answer here will be 0. But we could never allow for a number like 2 over 0, or even though 1,500, whatever, right? 1,005 over 0, regardless small or big. The reason because if you key in the calculator, as long as you divide by 0, it makes no sense. You don't have any number for you to divide, actually. And therefore, these fractions are not as it. You cannot have a value when the denominator is 0. So based on that, we know that this x value have to have a restriction for it. Because if it is the number, we see it right away. We say, this is 2 over 0. No, this doesn't make sense. Now, 2 divided by 0 doesn't mean it equal 2 or equal 1, right? Or equal 0. It's just undefined. So this fraction, we call an undefined fraction. And I'm going to say U and D here stand for undefined. From now on, a short form for undefined, UD, right? So we know that as long as the x fall into the category of 0, this fraction will be undefined. Now, for the number, we see right away, but for the x, how do you know, right? Because the x here represents any numbers. It could be a 0, or could be 1, or could be 2. We don't know. And therefore, to avoid the error mistake when we write the fraction, whenever we have a rational fraction, we should state x have to be different from 0. So this restriction always have to have, right, for the value of x. Now, the x here can be a negative. Let's say you have 3 over minus 4. You can write this as minus 3 over 4, or this minus in the middle, doesn't matter. But as long as the x is here, not the negative number, but the 0, it's not acceptable. So based on that, we keep in mind our characteristic of rational function. Now, obviously, if this is only one x, you can just state that x different from 0. The statement had to be there for this rational function. What about if it have a more than a number of x like this, or an algebra like this, or like this? Then we're not going to know. Yes, we state that x have to be different from 0, but even though this x here different from 0, we just state one x here. It doesn't mean the whole thing here will be different from 0, or the whole thing here will be different from 0. Obviously, you can see if you put a 0 in here, because x equals 0, then 0 minus 0, 0. But what about minus 6? You cannot change the minus 6 here become 0, because this is the original statement, the original question. And therefore, we have to learn how to manipulate the expression and to solve for what kind of value of x to make this denominator here, the whole thing here, become 0. And therefore, to solve for the value of x, to make this expression down here become 0, then we can make a statement something like this. Let's say if we have x equal, just for example, right, it not be accurate. If x here is positive 6, and then this positive 6 will make this become 0, then you will make a statement that x here have to be different from positive 6. But, and therefore, we will look into that later on, right? So now you understand that for the rational function, the first step, we have to realize that the denominator here cannot be 0, regardless whether it's a 1x value or a 4x value like this, or the x squared value like this. We cannot allow for whatever the value of x here, make the whole expression down here become 0. And therefore, we will aim for it in the next task I'm going to show you here. So let me go back to the basic function here, y equals 1 over x. So we state the restriction, we say x cannot be 0. So let's take a look at the our coordinate grid, right? This is the y-axis, and this is the x-axis. So we are going to sketch this basic function on this coordinate grid here. Usually when we sketch the function, we base on the table value, the data table, and then we plot the point, where's the x, where the y coordinate, then we connect them and we make a graph. There will be so many ways to draw a graph, to sketch the graph rational function by hand without using the graphing calculator. And we must learn in this course how to sketch it by hand. But then we can use a graphing calculator and check our sketching to see if we are doing right or we are accurate or not. So that's the way we learn in this course. Not just punching in the number in the calculator, graphing calculator, and then show here, this is the graph, right? we can use technology for the tools to how to incorporate in our mathematics for checking and easier to assist in mathematics. But we don't want to learn math in the way that our technology will replace the mathematics subject. Then in that way, it turns out that we learn technology. We're not learning mathematics. But my philosophy of teaching math means you learn how to operate on the mathematics level, scale. Technology can help it to improve our knowledge and to provide us more accurate data. And sometimes, yes, in some topic, we do replace it, using it, taking advantage of the roughing calculator for decimal numbers or something. But not entirely. We still have to learn the basic concept, the foundation of math. And in mathematics, only for learning elementary stuff in high school, they are already found basic stuff for the foundation. And they already have a lot of information for us just in order to learn the basic. So not even though have time to invent something fantasy, if we take time to create the fantasies, math fun and projects and things, yes, we can do that once in a while. But otherwise, it will take the whole curriculum away for just learning one step or one topic. So anyway, please allow me to express some food for thought in my lesson as well. And sorry for wandering around. Anyway, I'm going to get back right here. We are going to sketch this function on the diagram here. Now, usually we will learn some technique of sketching later on, not in this video. In this video, I would like to show you the analysis of rational function in terms of their basic characteristic and what do we pay attention in to find vertical asymptote, horizontal asymptotes. And what do I mean when I talk about asymptotes? So let's take a look at the data table here. I put it here, if x approaches to a large number, right? So these are the value of x along this axis, all the way from negative infinity, right? All the way to -2, -1, and then we hit a 0 right here. And we continue go for positive number 1, 2, and then here will be a large positive infinity number. And we have both of this for both the y and the x-axis. So down here will be negative infinity for the y, and up here will be a positive infinity for the y. So I'm going to demonstrate a few numbers on the scale and find out its characteristic. For example, if I put 10,000 here, it means this x approach to a very large infinity. And I just make a few examples, for example, 10,000. So what happens when you calculate the y? The y value will be equal 1 over 10,000, right? And it means that the y have 1 divided by big number, so the y value becomes 0.0001. That's the value. If we divide 1 by this x, right? Because this is the y function, 1 over x. So 1 over 10,000. Now the same idea, if this x approaches to 1,000, then what will y approach to? And I put the arrow, it means not exactly, but approaching, right? So the y will approach to 0.001 here. if it's 1,000. And for here, the y will be approach to 0.01. And here will be 0, right? And approaching, okay? So maybe put 0, 0, 0, 0, 1, something like that, okay? Now, what if the x approach to negative infinity? It means this side, right? When the negative number getting very large. So we have -2 smaller than -1 and smaller -3 and then -100, -1,000, something like this. So when x approach to negative infinity, which is on the side of the quinary, right? This line, number line here, then we have y equal 1 divided by -10,000. And of course, the answer will be exactly the same like this, except that it's in the negative value. So that will be minus 0.0001. This will be minus 0.01 and minus 0.01 and minus 0.000 whatever, right? 1. So this is the data table value. We calculated and we put it in there. Now, the next column, right? The next column, and I put them together. So maybe I should put a line here so you can see better. So in the next column, I describe the x and the y value. If x approach to 0, but on the positive side. So let's say here is our origin, right? 0. If x move over a little bit here, right? And for the first one, I talk about 0, 0. So of course, y will be approach to, if it is positive 0, a little bit. Okay, let's leave this for now. Okay, let's do the 0.1 and see what happens. Now, y will be equal 1 divided by 0.1, obviously, right? That is in the form of this, right? But I also can convert this, become 1 divided by 1/10, because 0.1 equal 1/10. Now, obviously, you know how to divide a fraction, which is the numerator here will multiply with the fraction upside down, so it becomes like this. And therefore, this value will be equal to 10. So when we divide a very small number, it turns out become a big number, opposite, right? So now you know this will fill up with the number 10 when we say 1 over this number. And similar like this idea, this will be 1 over, the y will approach to 100 if we divide 1 divided by this small number. And this 1 will be 111.11, blah, blah, right? When we divide like that. And this will be 111, 1, 2, 3, 4, 1, 2, 3, 4, like that, right? If you plug in the calculator. So now this is positive. What happened in the negative? Of course, this will be similar, except that in the negative value, everything will be negative, right? So that will give us negative 10, and this will be negative 100, and this will be negative 111, and negative 1111.11, blah, blah, so on. Okay, so based on this data table, we are going to sketch our rational function. And of course, it's just like estimating, not quite accurate because we're talking about approaching, but we still can figure out the graph, right? Okay, so let's look at when x equal to 10,000. Now, obviously, I don't have enough room here to express the number exactly 10,000, but we know that somewhere here, right, our graph will be approached, the x will be approached with a very large number on the side of our coordinate. And let's say if x approach to 10,000, what happened to our y? Our y will be very small number, right? Because 1 divided by 10,000 will be 0.0001. So if x over here, right? If x over this side, and this is positive infinity number, then the y is 0.001, very close to 0, but never approach to 0. So let's say about here, right? If x is getting big, smaller a little bit, let's say 1,000. This y is still very close, but maybe somewhere around here a little bit, right? Higher than a little bit, but still very close to the 0 level, right? Because this is 1 for y at this level, and therefore they are 0, even though smaller, let's say somewhere maybe up higher than this a little bit, but still very close to 0. And on the way from x is close to 0, the y is still very small, right? Still very small. Now, I forget to mention, what if the x equal 1? Then the y will be equal 1 divided by 1, isn't it? And therefore, it will be equal 1. So as long as x equal 1, then we also have the y equal 1. So let's mark that point right here, right? If x is 1, not 0, not 1,000, not 100, like that, right? We know that as long as x is big, then the y is small, right? The level from here to here very close to 0, but never touch 0. If x is 1, then the y become 1. So we can mark this point valid as 1 and 1. 1 for x and 1 for y. What if the x equal negative 1? Then of course the y also equal negative 1, right? So therefore another x here, if x is negative 1, y also negative 1. So we can mark these 2 points. And this point we call a invariant point, right? And why do we call it invariant point? So I'm going to say here invariant point. Invariant, it means not variant, right? It means they're the same. And exactly, if x is 1, y is 1, they're the same, right? And if x is negative 1, y is negative 1, they're the same. So that's we call an invariant point. Now, what else do we look at? So we look at here on the positive side of x, and we mark a few points like this. Now let's look at the negative point here. If x is negative 10,000, it means this way, then y is very close to 0, except that our y will be below the 0 because negative. So up here a little bit is positive 0, but down here is positive 0, right? So our point will be somewhere like this. And if I'm getting bigger a little bit, minus 1,000, so our y will be still close to 0, but negative 0, right? Because it's like 0.001. So obviously like this. And we'll leave the point here so that maybe I should mark somewhere here. Okay, so this is our point when we're talking about this table down here, right? Now let's look at an x when x approach to very small number. So let's say if x is over 0 a little bit, what happened to our y? Our y start getting number 10, which is somewhere up here, to 3, 4, 5, 6, 7, 8, 9, 10. It's up here somewhere already. I don't have enough room, right? Now, if X is getting smaller a little bit, what happened? We have 100, so up here as well. So now we just know that as long as X getting close to 0 here, then our Y have to start from positive infinity, because these numbers are very big, right? 100 or 1,000 up here. So therefore, we'll be able to shape our sketching now connecting to this point. It go to 1 equal here, but then its shape look like this. So that is our first branch. Now let's look at here. If X is getting close to 0 here on the negative side, then the Y will be get down here very big, minus 10, minus 100, minus 100, 111, minus 1,000, 111. So the Y will approach very big, large number down here. So along with this point which is plot, we can sketch our graph on the side look like this. So here you go. You see that our rational number already sketching, right? Like this. And this makes sense because we know that this line keep going up to 100, 1,000, whatever. And down here it get close to 0, and close to 0, but never touch the 0 axis. And here it get close to 0, but never touch. And then shape along with this point and then go down here, get to negative 100, negative 1,000, and so on. And so therefore, this is the sketching for our rational number basic one here. Y equal 1 over x. We also can say this is f of x function 1 over x like this as well, right? So now you understand the purpose of this data I show you and the sketching of basic of rational function based on this obvious calculation. So let me erase this so that we will talk something else beside this, right? Basic understanding. So let me just put here the basic one is y equal 1 over x. And we said x cannot be 0. So now let's analyze a little bit, okay? So based on the sketching, we can draw a conclusion that at x getting very large, positive infinity, y getting very small, close to 0, right? Close to 0. So I'm going to fill it in here. Y will getting to 0, but positive. So on the right-hand side corner, I put a little bit of positive there to show that the 0 here is on the positive, right? Above the axis a little bit. So as I get to negative, then the y will also close to 0, but will be getting to negative 0, right? And we'll put a negative 0 on top, right? Corner like that. Now, as I'm getting to close to very small value, let's say over 0 a little bit, 0.001, 0.001, like that. The y will getting very large value. So y will getting positive infinity. So I fill it in here, and you can see from this data table, right? Now, as x get close to 0 on the negative side, then the y will be very big, but the y here will getting to negative infinity. So this is the basic characteristic of our rational function. Now let me talk more about this a little bit in this video, so that I can provide you more and more information, right? Now, let's say Let's talk about the vertical asymptote and horizontal asymptote in here, right? What does it mean when we're talking about vertical asymptote? And what is a vertical asymptote for the basic graph here? Not even mention about these complicated rational functions. Just talk about basic here. What is a vertical asymptote here? Now, our vertical asymptote, so let me define the asymptote mean first, right? So asymptote mean the line, the straight line, or it could be a slant asymptote as well, such that any y value go to that or any x value go to that, close to that asymptote, only can get close to, but never can touch that line, never can touch that asymptote. And obviously, in this picture, you see this function never touch the x-axis. Also, if you look at just one branch on the top, right? We don't have this function touch the x-axis because some function might cross the x-axis and have a root. We call a root if it cross the x-axis, right? But obviously, our rational function is very special. One, this branch never cross the x-axis. It just keep going, right? Touch close to the zero, to the x-axis, but never crossing it. So we can define that the x-axis here is the horizontal asymptote of this function because this function never touch it, right? That is one horizontal asymptote right here. What else? Let's look at the vertical here. This function getting up here and very close to the y-axis, but again, never cross the y-axis. So this function doesn't have a y-intercept. Also doesn't have an x-intercept if we look at on the right-hand side. Now let's look at on the left-hand side. This function also never cross the x-axis, so we don't have x-intercept, as well as never cross the y-axis down here. So therefore, we can say that the y vertical here is the asymptote of this function. So for the basic function of 1 over x, right? This is the function, let me write down, this function y equals 1 over x. So for this basic function, we know that the vertical asymptote, and let me mark here, right? We have the vertical asymptote is the line x equals 0. X equals 0, because at this line, x equals 0, right? This vertical line here is the vertical asymptote. What about the horizontal asymptote? So we say horizontal, H stands for horizontal, A for asymptote, is y equals 0. It means as y equals 0, right? The value of y equals 0 right here, this is the horizontal asymptote for this basic function. Now, in some rational function like this one might be the vertical asymptote and horizontal asymptote no longer to be this value. It might be x equals 3 or negative 4, y may be equal negative 5 or y equal negative 6, something like that. And we will learn how to find the vertical asymptote as long as the horizontal asymptote in our lesson today. I think that might be this video is a little bit long, but let me just mention a few things for you before I end it, right? So we examine the lesson data, we know how to get the basic one. Now we understand what the vertical asymptote mean, what horizontal asymptote mean. Now, one more thing I want to mention. Obviously, you can see that at the vertical asymptote, we don't allow for the x equals 0. And here, this is the restriction, right? So you can see that as long as the restriction x equals 0 here, we also can say this is our vertical asymptote because we not allow for the function touching or crossing this vertical asymptote. So in other words, to define what is a vertical asymptote, we have to solve for the x down here. And we know in our basic one, as long as the x equals 0, if x equals 0, right, then this is our vertical asymptote, if x equals 0, right? And therefore, the restrictions say x have to be different from 0, okay? But the value for x equals 0 is a vertical asymptote. So basically, to find the vertical asymptote, we're going to set the algebra here equals 0, and we solve for the x value. So as long as x equals 0 in this basic function, then we know that is vertical asymptote. Also, we can say the restriction for x is x have to be different from 0. So when we do this, it means we mention this is the domain of the function. In this basic function, x can be any value all the way from negative to infinity, except x cannot be right here. It cannot be right there, right? And obviously, we don't have any function as such when the x getting close to this number here, 0. But x can be any number. So to state the domain for this basic function, you would say rational function before I end this video. So let's talk about this bar I divided. So these are the complicated rational function. We're not looking at it yet. We're looking at this one right here. So the domain for our rational function is any value of x from negative infinity to positive infinity, except the x cannot be 0. So x can be very close to 0, but never touch the 0 here. And therefore, we have a restriction here, x cannot be 0. So we just put in domain, say, a set of x, right? When we put in this bracket, it means a set of it, not just one value of x, but it could be x1, x2, or 3, right? A set of x such that this is plus stand for such that x have to be different from 0, and x can belong to any real number. And we close the bracket. So this is the x domain for this function. What about the range? So when we look at the range, we're talking about the y value, right? So the range stands for the y values. So again, any value of y can go from here all the way down here. It means from positive infinity to negative infinity, including rational number, irrational number, whatever, right? As long as the y is not 0 as well. So we can say it's a set of y such that y have to be different from 0 and y belong to on the real number, except this number. So that's how we state the domain range for our basic rational function, y equal 1 over x. In my next video, because I don't want to make this video so long, it will be overwhelmed for you. We have a lot of things in detail information, analysis, data analysis in this topic. So I would like to say this left bar here, when we get into the complicated rational function here, what do we do with that? So stay tuned for our next video. Thank you for watching, and bye for now.